So I'll be talking about my 15400 research project, which will be on regret minimization in continuous imperfect information games. I'll be working with Professor Sandholm in this project. Professor Sandholm is a professor here at CMU who specializes in imperfect information games. Just last year, Professor Sandholm and his PhD students were actually able to create the first ever agent that was able to beat professional poker players in Heads Up No Limit Texas Hold'em. So Professor Sandholm is on the cutting edge of imperfect information game research. So first we'll talk about existing regret minimization techniques. Regret minimization is a technique used to find Nash equilibrium strategies in imperfect information games. A Nash equilibrium strategy is a theoretically optimal strategy that is unexploitable. And imperfect information games are games like poker and StarCraft and business negotiations, games where the players don't have full information and there's hidden information in the game. The most popular regret minimization technique is counterfactual regret minimization, also known as CFR. The way CFR works is by iteratively traversing the entire game tree, playing its current strategy at each iteration. Initially, the strategy that it plays is completely random, but after that, regrets are accumulated on each action, and in the future iterations, the actions are played with probability proportional to the amount of cumulative regret on that action. So because it constructs the strategy in this way, it must store the cumulative regrets for every action in the entire game. Additionally, the strategy construction in this way is actually not guaranteed to converge to a Nash equilibrium strategy at all. Instead, the average strategy played over all the iterations is guaranteed to converge to a Nash equilibrium strategy. So for this reason, CFR must also store the average strategy played over every iteration. So some weaknesses of CFR, as we just mentioned, CFR has to store the cumulative regrets for every action in the game and the average strategy for the entire game. It stores these in tables, which can get very large as the game grows large. For example, in poker, the game of poker actually couldn't be solved in this way, and a extraction for poker, or a smaller game with similar strategic structure, had to be used instead. And even this abstracted game filled the entire memory of a supercomputer. So the memory taken up by these tables very quickly becomes the bottleneck of CFR. Another weakness of CFR is that because we use these tables to store the regrets and the average strategy, and these tables are inherently discrete data structures, CFR can only be used to solve games with discrete action state spaces. This is generally solved by abstracting games with continuous action and continuous state spaces into similar games with discrete action state spaces, but oftentimes a lot of information about the game is lost during this abstraction process. So now we get to my project. So in my project, instead of storing these regrets in average strategies in tabular form, they could be learned by a function approximator, such as a neural network. So this accomplishes, this fixes the weaknesses we just saw in CFR. This function approximator could effectively store these values in a much more compact representation rather than in the giant table that takes up so much memory. So it fixes our issue of taking up so much memory in the system. It also allows us to perform regret minimization over games with continuous state and action spaces, because we no longer have to discretize these action and state spaces to store in a table, and instead the neural network could take a continuity of action and state inputs and represent the respective regrets and the average strategy. There is some precedent for this work. Just a few months ago, a paper was released on arXiv describing how to perform counterfactual regret minimization with two neural networks, one to store the average strategy and another to store the cumulative regrets. Although this paper only did this for games with discrete action state spaces, so it would just aim to minimize the amount of memory used and get rid of the tables for that reason. But I would like to extend the work done in this paper onto games with continuous action state spaces to allow CFR to be used in these types of games. So that's my project proposal. Thank you.